Today we're going to continue talking about quadratic functions. That is a function, the defining characteristic of which is that there's an x squared term in it, and that's the biggest power of x that we have. So a quadratic function, the big thing is this x squared, or with this x minus h squared, eventually there'll be an x squared term in it. That's the thing, the square. All right. We want to think of functions in terms of the rule of 4, which means numbers, graphs, equations, and words. And last time we talked about the pattern in the numbers, and we characterized the pattern in the numbers by saying that the rate of change is linear. So a quadratic function, the pattern that we're looking for is that the rate of change is linear. So that first level of subtraction in a table is not going to be constant. It's going to be linear. So that second row of subtraction, the rate of change of a quadratic function is constant. That's where we get the pattern of addition. So the pattern of addition shows up in the second line, not in the first line. We also want to talk about the symmetry in the graph. This led us to view that the left side was just a mirror image of the right side. So the symmetry of the graph of a quadratic function is, we have this vertical symmetry. So the graph of a quadratic function is called a parabola. And so we could describe the symmetry in the graph of a quadratic function by saying that parabolas have vertical symmetry. What that means is that if we draw a vertical line through the vertex, the left side is a mirror image of the right side. All right. One thing I've noticed about these particular pens is that they have speed limits, but the speed limit is not dependent upon the style of ink that they're using, but the color of the ink. And some of the pens have a lower speed limit than others, like this light green pen, where I really like the color because it actually shows up as green in the scans. It doesn't show up well in the scans because it has a low speed limit. So to make it show up, I have to write slower and sometimes double write. So when we're looking at the graph of a quadratic function, we have this vertical symmetry. The left side is a copy, a mirror image of the right side. That showed up in the numbers, that the numbers on the left were the same as the numbers on the right. So this vertical symmetry means that numbers that are horizontally the same distance from the middle will have the same y value. So that's what we're talking about with this symmetry. So we have the same y value, this vertical symmetry. So points that are the same distance horizontally from the middle have the same y value. Or same y coordinate. That's what's going to give us that vertical symmetry. 1 unit away from the middle, we'll have the same y coordinate. Middle is the kind of common term that I will use to describe the axis of symmetry, which is a vertical line through the vertex. So the middle of the graph is the axis of symmetry. The middle is the axis of symmetry, which is a vertical line through the vertex. So the middle of the graph is the axis of symmetry, which is a vertical line through the vertex, and the vertex is the highest or lowest point on the graph. The vertex is the highest or the lowest point on the parabola, the point where the parabola turns. So parabolas come in two varieties. When we're thinking in terms of quadratic functions, where y is a function of x, we get two varieties of parabolas. Parabolas that I refer to this kind of parabola as a parabola that opens up and the vertex is the lowest point. Or we can have a parabola that opens down. These are just terms that I use to describe the two directions of parabola that we look at. So here's the vertex down here. And here's the vertex up at the top. It's either the highest or the lowest point. I refer to this parabola as one that opens up. And I'll refer to this kind of parabola as one that opens down. Sometimes I refer to them as happy and sad, because one is smiling and one is frowning. So the opens up parabola, we can tell which kind of parabola we're looking at, we're dealing with, just by looking at the equation. Remember, part of the rule of four is to not just know the four different ways of describing some algebraic object like a quadratic function, but to understand how those four descriptions are connected. So to connect, one way we can connect the graph to the equation is that we can determine whether a parabola opens up or opens down based on the sign of the leading coefficient, a. So if a is positive, then we have a parabola that opens up. And if a is negative, then the parabola opens down. So up is positive. That's usually two things that we put together. So it makes sense that I refer to this parabola as opening up, because it associates up with positive and down with negative. Just assigns the positive direction, which is what we typically do anyway. One of the reasons that I shy away from using happy and sad for my parabolas because I don't want to associate happy with positive and sad with negative, because those are just different states. One shouldn't be considered bad or negative. Sometimes sad is the correct response. All right. What we want to be able to do is understand what makes the parabola this rounded V shape. That's the other thing that I want to make sure that we think of. I don't want to describe these as U-shaped graphs. I want to describe parabolas as rounded V-shaped graphs. This is just a personal pet peeve I have because U's go straight up and down at the sides, and V's kind of have an angle. So we're just going to make a V and kind of round it off at the bottom. This is not also, V's aren't also very good because the V's are also just straight lines. So that's why it's rounded. It's kind of bent a little bit. So rounded V shape instead of U shaped. That's a personal preference. I'm sure that there are other professors out there who have a different set of neuroses than I do, and so they'll be perfectly fine with U-shaped. All right. What we want to be able to do is determine the vertex, because that's one of the most important points on a parabola. That's one of our important points. We need to be able to identify the vertex of a parabola. We know that it's the point in the middle, and we can use the symmetry. So if we have a table of values, we want to look for any 2 points with the same y-coordinate. The x-coordinate of the vertex will be halfway between those 2 points. So the x-coordinate of the vertex which I want to call h, is halfway between the x-coordinates of any 2 points with the same y-coordinate. Ugh, that's a mouthful. The x-coordinate of the vertex is halfway between the x-coordinates of any 2 points on the parabola with the same y-coordinate. And at this point, you're like, oh, why didn't you just say negative b over 2a? Because a, b, and c are not always the points that are the numbers that we have when we're describing a parabola. If we just have a table of values, we want to be able to find, we still want to be able to identify where the vertex is. So we want to look for 2 points with the same y-coordinate. So if I'm looking at a table of values, and I notice amongst my points, I have a point at 3 and y is equal to 7. And then later on, I see a point where y is equal to 7 again. And that happens at, I need to come up with a number and I'm coming up blank. That happens at like 9. Here are 2 points with the same y-coordinate. These are 2 symmetric points. The vertex will be halfway between. Halfway between 3 and 9 is 6. So that gives us the x-coordinate of the vertex. So I can use this to say halfway between 3 and 9 is 6. That's the x-coordinate of the vertex. Don't know the y-coordinate, I would need to have more information, but at least I know where the x-coordinate of the vertex is. If we're looking at the equation of a parabola, if we're looking at the equation of a quadratic function and it's in vertex form, then that form will tell us exactly where the x-coordinate of the vertex is. Oops, let's just go for the whole thing, because the vertex form, the vertex of f of x equals a times x minus h squared plus k is hk. That's why this is the vertex form, because it tells us what the vertex is. So for example, if I have a function f of x is equal to 3 times x minus 1 squared plus 5 has a vertex at 1, 5. For the x-coordinate, it's what we say after we say minus. So I say x minus, the next thing I say is 1, so h is equal to 1. H is what we say after minus. Sometimes general forms have a minus in them. Notice that we don't say minus k, it says plus k, so we just grab k as is. The plus 5 just shows up as is. So if I have some other quadratic function, let's say g of x is 5 times x plus 3 squared plus 1, then the vertex -3, +1. H is what we say after minus. And when we have x plus 3, we can think of that as x minus a -3. And h is what shows up, or h is what we say after minus. So we have to read x plus 3 as x minus a -3. So the x-coordinate of the vertex is -3. But k shows up as is. So k is just +1. So if I had a quadratic function that says, let's go with -1 times x plus 5 squared -3, then our vertex -5 -3. Because we read x plus 5 as x minus a -5. Notice that when we're determining the vertex, we're ignoring a in all cases. Note that we never care what a is. So for example, if I have some other quadratic function of smiley face times x minus 4 squared -7, then the vertex What we say after minus is 4, so the x-coordinate is 4, and k shows up as is. Doesn't matter what the leading coefficient is. The leading coefficient doesn't determine the vertex. The leading coefficient is just telling us what direction the parabola goes. We don't need the leading coefficient to find the vertex when the equation is in vertex form. However, when things are in standard form, we do need the leading coefficient. But fortunately for our heroes, there's a formula for that. Unfortunately for our heroes, there's a formula for that. The x-coordinates of the vertex of a quadratic function in standard form is negative b over 2a. So good news, there's a formula for it. Bad news, there's a formula for it. So if you have standard form, you can use h equals negative b over 2a. We get the y-coordinate by plugging in. So for example, if we have a function, say f of x is 3x squared minus 6x plus 7. I needed to come up with a number. I was drawing a blank. If we identify a, b, and c, then the x coordinate of the vertex will just be minus b over 2a. So here a is 3, b is negative 6, and c is positive 7. So the x coordinate of the vertex, h, is the opposite of b over 2a. So a negative 6 over 2 times 3. The negatives cancel out, and we end up with 1. 6 divided by 6 is 1, and negative times negative is positive. To find the y-coordinate of the vertex, k, we just plug 1 into the function. So k equals f at h. So k is equal to f at 1. So 3 times 1 squared minus 6 times 1 plus 7. So we get 3 minus 6 plus 7, 4. So the vertex is 1, 4. This is the first thing that we want to find when we're dealing with a parabola. The first thing that we should look for, the first thing that we should look for on the parabola is the vertex. For algebra purposes, the vertex is most important. One of the points that we're not going to talk about, which is an important point on a parabola, is called the focus of the parabola. So I don't want a whole new page for this, but if you think about what a satellite dish looks like, or if you watch a football game and you got the guys standing on the sidelines and they have those big circular microphones that are clear plastic. It was bad times before those things were made out of clear plastic, because you have to be able to point them at the sound, because we want to hear the sound of like the linemen running into each other. We want to hear that crunch when they run into each other, and like the ow, that hurts when they run into each other, because that seems painful. So they made that out of clear plastic, so the microphone operator can see through it and aim it right at where the sound is coming from. Also, so they can see when football players are headed towards them, they can see that they're going to be bowled over by a huge person being thrown to the ground by a bunch of other big people. So it's a safety thing. But if you think about the shape of that circular piece of plastic is just like your satellite dish. Now your satellite dish, if you look at it from the side, is in fact a parabola. It's a very kind of a shallow parabola, but it is a parabola. And it has a vertex. But the other thing that you'll notice, the satellite dish has this little arm sticking out, and it has a little box. That box it has the sensor in it. This is where the signal comes in. And that box is at a point called the focus. The reason that the focus is important is because parabolas reflect things in a very particular way. No matter where a signal comes in and hits the satellite dish and hits the parabola, it reflects towards the focus, no matter where the signal comes in. So it collects, a sound comes in, a sound wave comes along in and hits the parabola, or that little plastic dish. And because it's parabolic, it reflects towards the focus. So if something comes in closer to the middle, it still reflects towards the focus. So everything that's coming into the parabolic dish, even if it's coming like really close, it just scoots right by where that little microphone is. When it hits the dish, it goes right back to the focus. Everything reflects in this same direction. And so that's why it's really good at picking up sound. Rather than having a microphone, so that's where you would put your microphone. Rather than having a microphone where the sound would have to, if we didn't have that reflector, we just had the microphone all by itself, it will take the sound coming in, that line, it'll come in pretty well, but stuff that's farther away, it's not going to pick it up as much. Depending on how directional your microphone is, it's going to pick these background sounds up a little bit, but you're really going to have to be talking right at it to pick up in a sound wave coming in. But if you put a parabola behind that microphone and you put that microphone at the focus of the parabola, then all those sounds coming toward that hit the dish will be reflected back on the mic, and that will make a stronger sound. There's a great display of this in the Exploratorium. I don't know if y'all have been to the Exploratorium. If you haven't, you should go. Where across this big auditorium, they have these two big circular paraboloids. And when you stand in them, your head is roughly at the focus of those paraboloids. and they're pointed at each other. So you could stand in one and speak into the circular paraboloid. It's carved out of wood, and it's really nice looking. I haven't seen it for a while. I thought it was really cool when I was a kid. You speak into that, and all the sound gets reflected directly out, because if instead of a microphone, you put a speaker here, your sound kind of goes out in all these directions, but it gets reflected out straight out of the parabola. And so if you put another one of these things on the other side, it's going to take the sound coming in and reflect it back to your ears. And it's really cool. So you can have this conversation over this very crowded, very noisy place, but this sound cuts through because it's collecting a lot of sound wave and just sending it straight to the other one. It's a very cool demonstration. So the focus, where the focus is, depends on how curved the parabola is. But it is on the same line as the vertex. So the focus is sitting on the axis of symmetry. Anyway, that's fun fact about parabolas. And we're just taking a two-dimensional parabola and rotating it around in a circle to make a circular paraboloid. When we take a shape and make a solid out of it, we usually call them oids. All right. That's going to do it for today. What I want you to get from today is to be able to find the vertex by looking at a set of numbers, or find the vertex by looking at an equation. I want you to be able to find the vertex. That's just the middle of the graph. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.